Welcome back in another video tutorial from microbiology with Shagnik. So I am recording another lecture for after a very long time. So today we are going to discuss about UV visible spectroscopy. So remember one thing from spectroscopy, two things are very important. One is obviously our Lambert-Beard law. I have made a video regarding Lambert-Beard law earlier. You can consult this. And UV visible, the principle of the UV visible spectroscopy. Okay, so let's start our discussion regarding UV visible spectroscopy. So first thing that you need to know, that is what is spectroscopy. Then we will move on the UV visible spectroscopy. So spectroscopy is nothing but a instrument that will study the interaction between the electromagnetic radiation and molecule of interest. Okay, so I think now you may think that what is the utility of that process. So spectroscopy can help us to identify which kind of compound it is. Suppose if you have a solution and you are suspecting that inside the solution you have a compound A. Okay, so now but you cannot make it out whether it is A or not. So with the help of spectroscopy, by using a electromagnetic radiation, you can simply find out whether it is your compound A or not. Not only that, you can also find out what is the concentration of that compound. Okay, so how it is performed, let's see. So suppose, although atomic absorption spectroscopy is not in our syllabus, but we are going to use this picture to understand the basic concept of the spectroscopy. So as you can see that there will be a light source. Okay, so here we are using a flame, that is not our discussion, but make it clear that there will be a light source which will provide us the electromagnetic radiation. Okay, so this electromagnetic radiation will be monochromatized with the help of a monochromator. Okay, now you may ask that what is the utility of using a monochromator. So remember that from every kind of light source, the light usually in a polychromatic manner. Okay, that means it consists of electromagnetic radiation of various wavelengths. Okay, and for doing spectroscopic analysis we need to choose only a one kind of wavelength. Okay, we need to exclude all the others. So that is why we will choose a particular type of wavelength, that is this one, with the help of this monochromator. Okay, and this monochromator is designed in such a way that will only allow that wavelength of light that we want to use for our detection purpose. Okay, for example, we can use 260 nanometer wavelength for protein detection. Okay, so this is the lambda max value of protein. So we can use this to determine in any kind of protein sample. Okay, so that is the idea of monochromator. Okay, so monochromator will simply allow us to use a particular wavelength of our choice from a mixture of wavelength of light. So now, although here it is a detector, but in real, that means in our choice of interest or our spectroscopies that we want to learn as they are in our syllabus. So in those kind of spectroscopies there will be the sample. So our light will be passed through the sample. Okay, and remember that we have only absorption spectroscopy. So in case of absorption spectroscopy, some of the electromagnetic radiation will be absorbed by the sample. Okay, and the remaining will be just transmitted. Okay, that is the idea. So that means what? That means So now let's see this picture, that is a diagram for UV visible spectroscopy that we want to detect, want to learn. So this is the light source. Okay, so this light source will provide a polychromatic light. As you can see that there are 3 arrows. So from that, our monochromator, that is nothing but consists of slits, 2 slits and a prism, will allow only one wavelength of light. Okay, this wavelength of light will be divided into 2 parts. One will be passed through a reference cell. So remember, this reference cell is just a buffer or control. Okay, there are no sample present in that case, and another one is sample cell. Okay, so in both the cases the light will be passed. And now just try to understand that as it is a reference cell, that means in that cuvette, remember one thing, that in case of absorption spectroscopy we are generally keeping our sample in a cuvette. Okay, so the light passing through the reference cell will not be absorbed, right? Why? Because there are no sample present. So the intensity of the incident light means the light that is passing through the sample, and the intensity of the transmitted light, the remaining light of the what is transmitted light? Transmitted light is nothing but the remaining light that is passing through the sample after some of them are absorbed, right? Because remember, I0 is going through the solution and some of them are absorbed. Okay, and the remaining are just passing through, right? So these remaining lights will be known as transmitted light. So here the transmitted light and our incident light will be exactly the same, because the reference cell will not contain any kind of samples. But in case of sample cell, the picture will be different, because sample cell contains sample of our interest, right? So here we are referring the transmitted light as I. Okay, that is obviously smaller than I0, obviously, because it is contain less amount of radiation, right? So then the I0 and I will be detected with the help of a detector, and it is subsequently recorded. Okay, so now this recording will be in terms of ratio. Okay, this ratio is nothing but the intensity of the transmitted light, that is this one, by intensity of the incident light, that is this one. Okay, and I think you may now ask that it is also a transmitted light. Yes, obviously, but here we are not putting we have not added any kind of samples, right? So here our I0 is exactly the intensity of the incident light, right? So this our detector will give the value in the ratio of I by I0. This ratio is known as transmittance, that I have discussed in our Lambert-Beard law video, right? So I am again mentioning transmittance, that is, it is the ratio of the intensity of the transmitted light by intensity of the incident light, right? So now with the help of that ratio we can determine the absorbance of that particular sample. How? Because remember, we have derived a formula that absorbance is the inversely proportional of the transmittance, and it is not direct inversion relation, but the relation is logarithmic, right? So A is equal to log base 10 of 1 by t, that is the law, that is the formula that you can use for determining the absorbance. Okay, and also absorbance is determined by the path length of the sample solution. Okay, that is L, that is our Lambert law, and the concentration of the sample solution, right, that is C. and it is a inverse relation, it is a direct relation, right? A directly proportional to the concentration of the sample solution and the path length of the sample solution. Okay, that is our Lambert-Beer law that we have discussed. So remember, UV visible spectroscopy means here the electromagnetic radiation that we are using is of UV visible range. Okay, that means according to the electromagnetic spectrum, the range is between 200 to 700 nanometer. Okay, among them 200 and 200 to 400 nanometer is for UV, and 400 to 700 nanometer is for visible light. Okay, so that is the concept behind UV visible spectroscopy. So remember, the spectroscopy in which the electromagnetic radiation is UV visible, it is known as UV visible spectroscopy. Okay, another thing that I would like to mention you, that whenever that electromagnetic radiation is passes through a sample, okay, the sample will absorb some of that electromagnetic radiation, right? As I have told you, this is the basic formula in case of absorption spectroscopy. So just think about it, whenever we eat something, we gain some energy, right? So here the case is exactly same. The sample will gain some energy, okay, that will cause some changes in it. Okay, and in case of UV visible spectroscopy, the change is electronic change. Okay, this electronic change is due to the transition of its valency electron from the lower state to the higher state. Okay, that is just like, suppose you have eat something and you are and as a result you are excited. That is the case in case of the sample here too. After absorbing or after eating the incident light, the samples become excited, and as a result one of the electrons present in its valency or the valency electron undergo a transition from its low energy state to high energy or excited state. Okay, so this kind of transition is known as electronic transition, and make it very clear that it is only the phenomenon for UV visible spectroscopy. If you are talking about infrared spectroscopy, that is nothing but here we are using a electromagnetic radiation of infrared ray, then the picture will be completely different. There, in that case, the samples present in the sample solution will absorb, after absorbing the electromagnetic radiation, will observe some change in their vibrational energy. Okay, that is known as molecular vibration, that we do not want to discuss here because our topic is UV visible spectroscopy. So that is the thing. Now we are going to discuss about the kind of transition, because remember, as our deal is with organic molecules, so organic molecules have three distinct type of electron. Okay, one is sigma electron. So remember, sigma is for mainly single bond containing molecules, for example C, single bond C for example, and pi electrons are also there for C double bond C kind of case, and C triple bond C kind of case. That means where you are finding any kind of double bond, triple bond, you can make sure that here pi electron is present, and the another one is N, that is non-bonding electron. So the N can be found in case of heteroatom. Heteroatom means C along with C and H, if you find any kind of O, N or halogen containing type molecules, then you can say that there will be the presence of N electron. So as I have told you that UV visible spectroscopy facilitate transition in the valence electron, so those electron will undergo transition, right? That means sigma electron will go from its lower energy state to higher energy state, pi electron and L electron also. Now my question is, how this transition is determined. That means either sigma will undergo transition, or pi will undergo transition, or n will undergo transition. How it is determined? So remember one thing, it is completely determined with the help of the energy of the electromagnetic radiation. Okay, that is mean that totally depends on the type of food we are eating, right? If we are consuming any kind of junk food, so we are more excited rather than eating some healthy diet food, right? So that is the case here also, because here the type of electromagnetic radiation, the energy of the electromagnetic radiation will determine what kind of transition will going to occur. Okay, so let's discuss about those kind of transitions. Okay, so that is the sigma, pi, n, pi star, sigma star. This sigma star and pi star are known as antibonding orbitals. Pi and sigma are known as bonding orbitals, and this n is along known as non-bonding orbitals. Okay, in non-bonding orbitals you can find lone pair. In case of normal bonding or bonding orbitals, it contains normal bonding pairs of electron, and these orbitals are normally empty. We don't need to bother about those things. So remember, so there can be 4 type of transition occur depending on the type of energy of the electromagnetic radiation. Okay, so if the energy is too high, okay, so it will cause transition of sigma to directly at the top level, that is sigma star. Okay, that is when the energy is too much high, that is when the energy is highest. That means sigma to sigma star transition, that is known as. Okay, and this transition is also known as transition from HOMO to LUMO. So HOMO means highest occupied molecular orbital. Okay, and LUMO means that is not lower, that means lowest, it will be lowest unoccupied molecular orbital. Okay, so when our energy is high, not only high, the highest, we should expect a sigma to sigma star transition, but there is a condition. Okay, so suppose you are dealing with a molecule that do not have any kind of sigma bond or sigma bond. Okay, so in those cases you may not observe transition, although sigma bond is most common, right? Because in case of single bond you can find sigma bond, in case of double bond you can find sigma bond, right? So but if in case of N, that is mainly observed, suppose we are dealing with CH2, so it is not a non-bonding electron. There is no non-bonding electron, because I have told you, when you get something except C and H, then you can go for N. So they are not heteroatoms, right? So are they exhibit any kind of transition from N to pi star? No, because there are no non-bonding electron present in their valence electron, right? So there will be no N to something transition, right? So the second highest transition is, that means when your energy is second highest, then it will observe N to sigma star transition. Okay, then subsequently pi to pi star and N to pi star. That is the order. So sigma to sigma star, then N to sigma star, pi to pi star, and last one is N to pi star. Okay, you can simply remember this, that the power of sigma is high, so you need better energy or more energy for undergoing any kind of sigma transition, right? So sigma to sigma star will be higher, then N to sigma star, then our pi to pi star, and N to pi star. And you can also remember that similar transition require greater energy, so that the order can be easily remembered in such a way. Sigma star, I have told you that sigma require more energy, so sigma star. N sigma star, because presence of pi do not affect cannot require but or cannot demand more energy than the sigma star, right? So n sigma star will be the second one, then pi star, because I have told you same type of transition will require more energy, and at last n to pi star transition. Okay, and remember the first two things are bonding orbitals, then non-bonding, then anti-bonding. Okay, so in anti-bonding are normally empty, in non-bonding you will have lone pairs, and in bonding orbitals they contain normal bonding pairs of electron. Okay, and the order of the transition is important to remember, that is sigma sigma star, n sigma star, pi star, n sigma star, n pi star, sorry for that. So that is how the transitions are going on. So I will come back to that picture within a minute. So that is how the UV visible spectroscopy help us for measurement. Okay, so suppose you have added here paracetamol. Okay, and now you will get the I0 ratio, that is the transmittance value. With the help of transmittance you have determined the absorbance, right? And you know what kind of wavelength you have chosen, right? So with the help of this thing you can simply find out whether it is your choice of interest or not. Okay, because absorbance you have determined, you know your absorbance value, and now with the help of those peaks you can find out whether it is your choice of interest or not. Suppose we have a sample that contains impurity, but here it is the standard raw result. Raw result means in that particular spectrum the sample is exactly pure and we have the exact absorption spectrum, right? And after detection with the help of UV visible spectroscopy we have obtained a result that contain additional peak. Okay, because here we have observed only one peak, but our sample of interest that we are examining contain one extra peak. What does it mean? It simply means that it contains some impurity, right? Or it contains some extra functional group that showing absorbance, right? So in that way we can determine the impurities of a sample with the help of our UV visible spectroscopy. The process is same. In the sample cell we will keep our sample of interest, then we will perform the same thing, we will get the I0 ratio result. With the help of that we will determine the absorbance, then by yielding the absorption spectrum we will compare the absorption spectrum with that standard absorption spectrum. Okay, and then we will get our desired result, that whether the sample contain impurities or not, right? So that means what? That means that this technique is quantitative as well as qualitative, right? It can tell you whether your sample contains any kind of functional group or not. Okay, so suppose you are expecting a functional group and you know at what wavelength the functional group will absorb maximum. Okay, so in that particular wavelength you will expect a peak, but if you cannot get your expected peak at that particular absorbance, then you can conclude that yes, my sample do not contain that particular functional group. That is the idea how we can determine whether our sample contain a particular functional group or not. We can find out impurities with the help of that, along with both quantitative and qualitative measurement, right? And with the help of that UV spectroscopy we can also determine kinetics of the reaction. Okay, suppose in a mixture a particular reaction is going on, okay, and you passed, let me change the color, a UV radiation through that sample. Okay, so all the molecules will show absorbance, and now by simply determining the change in absorbance you can study the reaction kinetics. Okay, so that's how with the help of UV visible spectroscopy we can perform various things. Not only that, you can also ligate our UV visible spectroscopy with HPLC, considering it as a detector system, right? So that's how much important UV visible spectroscopy is. It can give you the identity of a sample which absorbs UV or visible light of 200 to 700 nanometer. It can give you the details of that sample, the concentration of the sample, because remember, suppose you are determining a protein and protein show absorption maximum at 200 nanometer, but you have used a high amount of protein, then absorption maximum will be same, but it will be absorbed morely, right? Absorption will be more intense. So that in that way they can also give you the result of concentration. Not only that, molecular weight determination of sample can also be done with the help of UV visible spectroscopy. That means what? Any kind of sample that absorb UV visible wavelength radiation can be detected and can be analyzed with the help of UV visible spectroscopy. Okay, now let's look at the principle. Although we have discussed, so basically it is nothing but the reaction of interaction of the light and matter. Light means electromagnetic radiation, okay, EMR. So energy absorbed in the UV visible region will produces a change in the electronic energy of the molecule, okay, resulting from the transition of the valency electron. Okay, so the distinct type of electron involved in the organic molecule are pi, pi star, sigma, sigma star, okay, and N. So depending on the type of energy, as I have discussed with you, absorbed by the chemical substance, fourth type of transition will occur. Sigma, sigma star will be the more require more energy or highest energy, then N sigma star, then pi pi star, and then N pi star. And the order of transition depending on the amount of energy required: sigma to sigma star, N sigma star, pi pi star, and N pi star. The absorption of the ultraviolet light by a chemical compound will yield a distinct spectrum that will give us the identification of the compound. Okay, so that is the application part that I have discussed with you. Okay, presence of heteroatom. Presence of heteroatom means what? If our sample is undergoing any change that involve N, that means N to suppose sigma star transition or N to pi star transition, then we can conclude that yes, our sample contains heteroatom. That is why it is undergoing such kind of transition, right? And can be useful for quantitative qualitative determination. Yes, we have discussed presence or absence of functional group by determining the absence of band at particular wavelength, right? Kinetics of the reaction and many drugs, raw material or in the form of formulation we can conclude, right? And molecular weight detection, UV spectroscopy can be attached with the HPLC. So that is the concept behind UV visible spectroscopy. So I hope this video will be helpful to you, and if it is, please hit the like button, share with your friends, and subscribe to my channel to get more videos like that. And thank you for listening to this class.